Okay, so again, if this is tiny in comparison to that, we can say this is essentially 0. And so then we could do 1 minus 0 would be 1, and the square root of 1 is 1. And so you'd have time naught divided by 1, which would just be time naught. So time naught would equal time. And so we don't see this big discrepancy between the two when speeds are slow compared to the speed of light. But as we increase this speed of light, let's run a number and let's see. So let's say we're going to go half the speed of light. Okay, so we would have 0.5 squared divided by the speed of light squared. Okay, 1 minus the 0.25, and then the square root of that. And then time naught, should we say an hour, 60 minutes in that comparison. Let's do 1 minute, let's do 60 seconds. So more time has passed than what was observed by the person inside the spaceship. Couple important key concepts with this. Now, if you watched that twin paradox video, more time passed for the person viewing the spaceship than the person in the spaceship, and that was supported kind of by that video there. Now, oh, we talked about that. Okay, let's keep going. If the value of the speed is greater than the speed of light, then the change in time over the change in time naught would be imaginary. Okay, and so it's this argument that something cannot go faster than the speed of light. Speeds greater than the speed of light have never been observed in nature. Experiments have shown, though, that time dilation predicted by special relativity is correct. Okay. There was an experiment, I should look into it, but it was an atomic clock with great precision that they took onto a jet airplane and flew around the world or something like that. And the difference in the two clocks, the one that was left at the airport and the one that they took up in the jet airplane, was detectable. That it wasn't noticeable to any like human perception, but there was a time dilation that was observed and experimentally recorded. Okay. I'm not going to spend a whole bunch of time going through the twin paradox things. I'm going to hit a couple key points. What I really need you to do, if you haven't, is go and watch that TED Talk video. It was only like 6 minutes about this, because I think it does a really great job of explaining what's happening. Okay. We can use, like I said, that equation to show this as well. We can say that, so we have Ted and Alice. This time, again, Alice is in our inertial reference frame. She's stationary, and then Ted's going to travel with a velocity almost the speed of light, 0.9 the speed of light, to the star and then back. Okay. So what Alice measures is 2 times by 8.6 light years. Okay. And then divided by that 0.9 velocity. And that gives us a time component of 19 years. But what Ted measures is this velocity divided by the speed of light, right? And then this T naught value would be 8.3. And so the question is, what is correct? Are we seeing 19 years passing, or is it the 8.3 years? So in our earlier calculations, Alice would conclude that Ted will be younger than she is. Ted calculates the Earth, and Alice too, to move away from him at the 0.9 c, or almost approaching the speed of light. And so he would conclude that Alice would age 8.3 years while he aged the 19 years that the trip took. Ted concludes that Alice will be younger than he is. And then it talked about in that video how Alice is actually correct because she remained in the inertial reference frame, that even though Ted traveled at a constant velocity, he turned around, that a change of velocity vector is both magnitude and direction, and he changed the direction component. So if we're going to change velocity, that's an acceleration, so we're no longer in an inertial reference frame. Okay. Now this time dilation is also observed in satellites, that they're moving at velocities that we can observe that time dilation, and it does have to be taken into consideration, or it can throw off locations and dimensions. Okay? And then the last thing that we're going to address is length contractions. And again, I want you to make sure that you watch that video, not the twin paradox one, but the general relativity versus special relativity one. And it talks about, gives an example of a taxi with length contraction. And so if we're observing something moving close to the speed of light, we actually view it as contracting, being smaller in the direction that it was traveling. But then the opposite is occurring for the person traveling at that speed. The world around them seems to stretch out. Okay, and so it's really interesting to think about, because we have made these observations, Star Wars, Star Trek, and it seems like as they approach warp speed, or whatever they call it in Star Wars, that all the stars seem to lengthen around them. And if we were viewing it from inside the ship itself, that would make sense. But if we're viewing them from outside the ship and we're watching the ship travel away, we wouldn't view the ship lengthening. We would view it contracting, which is opposite from what we usually see in the movies. Typically in the movies, when we're watching the ship speed away at speeds approaching or greater than the speed of light, which is another issue, right? But that it lengthens, but really we would observe the exact opposite. We would observe it contracting. And with those observations of the movies made inside these spacecrafts, when they look at the stars seem to lengthen, right? We see those streaks of stars. That's more accurate. If we're traveling at that speed compared to the relatively stationary stars, that we would view the outside world as lengthening. So I got it half right. So note, it's important to point out that everything we've talked about is about in special relativity is going at a constant speed and not under the influence of the acceleration of gravity. So be mindful of that, and then we will address some general relativity concepts where we do have that acceleration or a gravity component on learning target number 5. Okay, awesome. The assignment's posted. Let me know if you have any questions.